4.
Yep. All right, good afternoon, everybody. Welcome to today's weekly College of Engineering, UAA College of Engineering seminar. For those of you who don't know me, my name is Dr. Scott Hamill. I am the structural engineering professor here at UAA, and I'm very happy to introduce today Amy Mestes from Respect, who is going to talk about the Houston High School, which is timely. I'm excited.
Okay, I didn't do like an intro slide on myself, but like you said, I work at Respect Engineers, and I've been there since 2005. When I got out of college, we were PDC first, and now we're Respect. And I've been a structural engineer that whole time, but right now I'm also in charge of our facilities group in Central Region. So I get to interact with all the kinds of engineering, not just structural these days, which is a good time. So we like to give each other a hard time, but it's a good time. So what I'm going to talk to you about today was the Houston High School project, but taking a little of a different slant on it and looking at what the life of a project looks like, and not just the design part. So like I said, Houston High School, this is the Revit rendering that we had when it was done from the architect. It was a multidisciplinary project. The architect was PDS Architects, and they were the prime consultants on the job, with Respect doing the structural, electrical, and mechanical designs for the facility. So what does the life cycle of this facilities project entail? Somebody has to think of it first. The project starts out, and then they got to find a consultant to do the work. And then where we come in is we design it, we do all the work. So we heavily live in childhood and adolescence of a life cycle of a building. And then they award it to a contractor who's building it, and then we come back in and provide support while it's getting constructed through construction administration process, and then it gets used. And hopefully this project or this process gets reincarnated and starts all over when they need to revamp their mechanical systems or their structure as new codes come along and we learn more and new systems need replaced. So right off the bat, the project is born. A client decides they need something. In the case of this project, this is the Mat-Su Borough, and they needed, what they thought they needed was the Houston Middle School to be repaired and a part of it to be reconstructed. So the scope that went out to the world was that the Houston Middle School was damaged in the earthquake. They wanted to demolish 1/3 of the building, the academic wing, and repair and reconstruct the administrative and gym wings of the building. And they wanted it done in 3 months. So that's what went out to the world, right? I know everybody's like, what? That's crazy. And it was kind of crazy. So then they have to pick a team. So how do they pick a team? They put out a request for proposal document through the public process, and they solicited design teams to propose on their work. It was a qualifications-based selection process, so there was no fee included in that effort. It was all based on our qualifications to do it, and the price was negotiated after the design team was selected. So we teamed up with BDS Architects, who we've worked with a ton over the years and have a strong resume for experience on schools. And then we had done a lot of earthquake repair work. And in addition to that, we'd opened a Mat-Su office, so we had some regional representation. So it ended up kind of being a perfect fit for what the Mat-Su Borough School District needed and our experience and expertise. Specifically, the earthquake response, we think, was a big portion of what we brought to that project. There's Jake, there he is sitting in the audience, but he's also in that picture. We looked at well over 250, I think that's kind of an old number, of buildings, from little tiny, we're scared about these sheetrock cracks in our house, to big structural problems that needed renovated in facilities. I think every structural engineer in town didn't sleep for a good year because we were pretty busy. But one of the things that we were proud of at Respect was that we were willing to speak up and talk to the press and be a part of that repair effort throughout Anchorage. So we attended the earthquake symposium, went to a ton of different meetings, met with MOA and FEMA and all, and NEHRP, and spoke up to the media and talked with homeowners about what they could do to repair their homes and where there was damage. And it's not always a popular opinion to say there's damage out there, but we're proud of what we did in that response. So, all right, then we get into things get real here. The childhood and adolescence, where all the real change and who you're going to be when you grow up happens. So for the Houston High School design progression, we had investigation phase of all of the earthquake damage. Prior to us getting involved, the firm that went out and looked at it right after the earthquake only had 2 days time to look at it, and they only had about 6 hours, which for the size of this building is just nowhere near enough time, right? So that's what their RFP was based off of. So definitely no judgment on the team that looked at it, because it's pretty hard to look at a facility in that amount of time, which is where the recommendation had come from. So once we got through that investigation of all the earthquake damage, the second phase that happened for us was recommending they condemn the building instead of repairing it like they planned. And then we rescoped the facility and did a new design. It definitely took longer than 3 months, but it was way faster than we would traditionally do a project like this. And then we went ahead and did the design and a complete demo of that old building. So that's what we're going to walk through next. So just a few pictures of damage here. This project, I was like, I don't know, do I have a pointer on here? No. I bet I got a pointer on here. Can you see that? Yeah. Okay. So this is the library of the school. A ton of, obviously there's books everywhere, but a lot of ceiling damage, secondary architectural, mechanical, and electrical components saw a lot of damage throughout the school. This picture up here in the top, this scaffolding is actually supporting the main gravity beam in the academic wing. And this was present in all the classrooms on the second floor along the entire building, because I'll show you a picture later that explains the because and why it had to be supported. But one of the end connections had pretty much exploded the CMU and was rotated and didn't fall down, but it was on the verge. So they came in and supported this prior to allowing people to come in and do a full investigation of the building. Lots of this going on around the school where there was just CMU that had blown out and had problems. That's a wood block in there, which is definitely not how CMU should get built. They had laid a couple of 2x in the on-beam space instead of putting grout in there. So we found a lot of that going on. And then this one was just kind of interesting. We did not see a lot of this around, but this is a horizontal brace in the roof structure. So where the connection happened and one brace had to go through the other, that steel T had deformed and pulled apart during the earthquake. It also sheared one of the bolts off. If you can see that, there's a missing bolt there. One of the maintenance guys was carrying that around in his pocket when we were out there during our first inspection. So he's like, oh yeah, I got the bolts. I was like, I wonder what the grade of the bolts are. I'm gonna get up and get one. He's like, you can test this one. Okay, awesome, thank you. So it was kind of an interesting process. We got to spend about 60 hours in there doing full scale inspection and really looking at everything with mechanical, electrical, civil and structural engineers and the architect, and really dig in and find out what was going on within this building. So some more things and reasons of why we went down the condemn the building route. This picture is the bottom of a white flange beam right here that's supposed to be welded to a plate to drag load into the top of a bond beam, but some of these are hard to see, but this is the weld. Okay, it's supposed to be a full length weld, and you can kind of tell in this picture that that plate and beam have actually rotated relative to one another due to the earthquake. The quality of the grout in there, poor to say the least. You could basically kind of like reach your hand in and grab chunks out of the wall. So the connectivity of the roof and the floor structures into the shear walls was suspect in a lot of locations. So once we started looking through all of this, based on the things that we actually could see and find without destructive demolition, just that cost estimate was coming in at pretty much equal for the cost to repair it versus the cost to replace the building. It was a little more expensive to replace it, but we're talking like $500,000 on a $30 million project. So it's really close, and we had a lot of conversations and talked about, this is what we can see, right? So we're gonna come into contact with a lot of things that we can't see yet on this building that are gonna need to be redone. And we've done enough other projects that are retrofits. I'm sure a lot of us in this room have, where there's change orders in construction because there's a lot of things that you just don't know until you start looking. So the damage that happened in this facility was far greater than it should have been for the magnitude of earthquake that we had. So definitely looking at what would have happened if it had hit design earthquake magnitudes, and probably would have been catastrophic failure and loss of life in that school. So we're grateful that that did not happen. Some specific things that were going to be high dollar ticket in repairing this school. The CMU is partially grouted, and it was oddly partially grouted, like it would have 4 number 9 bars every 4 feet instead of having a bar in every cell, kind of a thing. It was just, they kind of spread out the grout as much as possible, and then you can see from the photos, and then the quality of grout was pretty suspect. There were a lot of locations where there was unreinforced concrete footings, so you couldn't count on them for any sort of uplift capacity when looking at this building trying to overturn due to seismic forces. And then it had a lot of wood diaphragms, which wood diaphragms are great, but the spans were way too long for wood diaphragms to be able to handle the expected loads. And a lot of this was, the wood diaphragms would have been fine at the time it was constructed, but they were damaged now. So when you are trying to repair something that's damaged, you can't, well, maybe you can't, you shouldn't just fix it. So that's where we're at with that one.
How old was the school?
Early 80s, so not really that old. So here's the beam seat I was talking about. So this photo shows you, these are the main beams that spanned the classrooms upstairs in the academic wing. This is the end seat. Those anchor rods went into one CMU cell, did not have any rebar overlapping into the cells adjacent or below them. They basically deformed under the load and blew out the concrete around them. They all looked like this. So what you're seeing in the picture is not my recommended solution, but this is what the insurance company thought that I should do to fix it, which was just throw a couple bars in there and epoxy them in, and I will quote, back butter the connection and move on with life. That was what they planned to do. We were like,
Were they gonna stamp it?
yeah, exactly. I was like, no, we actually had a conversation where I was like, would you send your kids to school in this thing if that's what they did? And he's like, yes. I was like, you are lying. So it was a good one, but so needless to say, with conversations back and forth, at the end of the day, everybody agreed this was not a viable solution for tying the main gravity beams back into this wall that clearly was not tied together well in the first place. And if we were going to do it, there would need to be some FRP solutions involved and make sure things were actually tied together. And that's where we came up with some of these high dollar numbers, is that the FRP solutions get pretty expensive pretty fast in order to make it work. Plus, getting enough testing done to know what materials we had in the building and be able to move forward from there. So we went down that road looking into testing and FRP and all of that before we made cost decisions. But these were alarming, right? You walk in and you see this up in a building, you're like, ooh, which is why the academic wing had originally been thought, they were planning to demolish this part. So that part was already in the works. So here's a couple more that just talk to the quality of the building as it was built, okay? So over here on the left, this is connecting the wood diaphragm to the bond beam. So I don't know what the structural value of insulation is, but I don't think it's gonna do a whole lot. It did, there was some movement here where that roof diaphragm was moving relative to the shear walls, because clearly there were lots of places where it was not connected. So basically it's a J-bolt in there, and there's some rebar. You can see there's some grout over there, happened. There's a big long stretch of like 25 feet right here where it's just sitting into nothing. Then you come along over here, and this is a partition wall, CMU wall. It was about 22 feet high. Up here at the top, you've got the CMU blocks that are just literally starting to come out. Some of them had already fallen down the wall, but it's really hard to tell in those pictures what's going on. So I grabbed one where it's partially falling off. These didn't fall off. The ones that did fall didn't fall off during the earthquake. They were falling off during the aftershocks. So hopefully nobody's in the building when any of that was going on. This wall was interesting because we knew it was going to be demolished. It was slated for that right from the beginning. So everything okay?
Yep.
All right. So we wanted to see if in this wall it truly had 4 number 9 bars in a CMU cell. So we went in and took a sledgehammer to it. Not me personally, but one of my coworkers did. Took a sledgehammer to it, we busted it out, and had 1 bar in the wall instead of 4. So we had done rebar detecting to find out which ones had bars, but it's pretty hard from that. The quality of rebar detector we had wasn't going to tell us exactly what depth it was and how many are in there because they're too close together to get a good read. So that's why we busted it open. So one instance where it wasn't right doesn't mean it's not right everywhere, but again, calls into that question of what else, what are we going to find when we open things up? What's going to happen? That probably happened in a RFI during construction where the contractor said, are you crazy? We can't put 4 number 9s in a single CMU cell, which I agree. And they're like, oh, well, let's just do 1. It's a partition wall. It doesn't need it. But it kind of calls into question when you're doing that retrofit and you're having to use as-built for what's in there. It was going to get to a point where we're going to need to do a lot of destructive testing and find out what was really going on in the building compared to what we had in the drawings. Oh, I guess I didn't talk about that last one. These are partition walls too, and we saw a ton of this where one wall is just pulling away from the other. This is happening all over the building. So fixable for a partition wall, but it's just going to open up again unless you do something that's an FRP solution or steel plates. See, again, back buttering, which I'd never heard before this project. We did not consider a viable option to just throw some grout in there and call it a day. So, all right, we have some really fancy beam pockets here where this is in the administrative part of the building, the center core of it, where they would put that beam in there. It's likely attached the same way as we saw the other ones, where it's got those studs down into the top of the grout, but then they backfilled that grout with grout and plastic. Lots of plastic shoved into walls and grout spaces we pull, or insulation or wood. So what this really is telling us is that the inspection that typically happens during CA didn't happen, which in the 80s in our area, it's very, very common for the inspection to not happen because it was the oil boom and it just didn't happen, right? So they were out there building and nobody was paying attention to some of it. So this is in the gym. This is another example of a wide flange beam main collector element that has bolts. They're on the other side of this flange, so you can't see them, but this is the side where you could see that it's hollow instead of grouted into that top load. And the roof was moving relative to the wall, but the shear walls were never getting loaded, which may actually have been a blessing in disguise in this earthquake, that there was no forced really transfer and a lot of energy dissipation happened through relative movement of the 2 elements.
So it's seismically isolated.
It's kind of seismically isolated a little bit. It's got some friction going on. You know. So the image on the left, this guy is what the original scope was. Okay, the red part is this part we're going to demo. That's where those bad beams were located that we were looking at. And the blue part was what we were going to retrofit, okay, and what we were going to fix. So along this primary line over here, along this line over here, were those pictures I showed you where the roof structure was connected to walls that didn't have grout. So primary load resisting elements that were lacking in grout. And fixable, sure. I mean, we can fix anything given enough money, right? But can we fix it to a high enough safety factor that we're gonna be comfortable with people going back into this building? Not without a lot of money, for sure. So this one over here is where we went with it. We did have a fast track design schedule. We got the design done, I wanna say in 9 months. It was quick from start to finish. But part of the reason we were able to do that is because the architects and engineers, we were all on the same page that we were replacing what they had. They liked the flow of their building overall, just wanted to tweak a few things. So as you can see, it looks really similar to the building that was there before. So some of the things they did, they went with centralized heating, so the HVAC, all the equipment and everything, not all, most of the equipment for mechanical and electrical ended up located in the central core and then being able to feed the rest of the building, which was great. This is what we ended up putting together at the end of the day. This is the academic wing. It was reprogrammed to be a high school instead of a middle school with a CTE focus. So they have a shop in the back and tons of classrooms dedicated to different types of learning that are not just your standard classroom. This is the gym over here. They're really excited about their gym because it's their main community gym and their main center to go do activities. When we started, it was like, build us a gym and then finish the school because we want that. But at the end of the day, it was just way more cost effective for them to do it all at once instead of phase it. And then the administrative wing, this lower area is where the principal and the nurse and all the other counselors and administrative functions happen for the school. And there's a cafeteria and a stage and all of that going on in the middle here. This is the structure. This is these are renderings from our Revit files. The bracing in this building is buckling restrained brace frames. Houston actually has 50% higher seismic loads than Anchorage does because they're close to the fault. They're 7 miles from the main fault line out there. So the earthquake loads were significant, and this really allowed us to lower the cost of the steel system and provide them a really robust system. You can see there's redundancy in this building. We were not going to leave this community without redundancy in their brace frames, and that was one of the goals of the structural design. Here's a look at the heating, ventilation, and plumbing systems throughout the building. You can see it all starts here in the middle, branches out, and man, those ducts were awesome. They're big. There's pictures of them later. They're fancy. And then here's the equipment, so you can kind of see the centralized look of it all. This is the electrical system throughout the building, which most of it is what you're looking at is the lighting effort that's everywhere. Too much to say about electrical. Sorry if you were an electrical engineer. So this is all of it combined together. The main reason I included this slide was just to talk about, like, part of our QC process is to do a walkthrough of the section cuts. So we basically start along this side of the building and just incrementally walk through and look. Do we have, and the architectural is also turned on at that time, right? Do we have anything that's colliding? Because, oh man, it happens when we're all doing our thing. Like, not on this project, but a good one lately where the ductwork was going through the elevator shaft. So we got a good check out of that. So it was like, well, it's only gonna get damaged once, right? Yeah. So we're able to just nab that and move on, right? And we do it both directions, looking through the building, get different eyes from different disciplines looking at it, and come out with a well-coordinated product that's easier to build when we get into the construction phase. Let's see. Okay, so design was done. Okay, let's build this thing. Who's gonna build it? So they are a public entity, so they put it out to bid. The low bid contractor is gonna get it unless there's any big concerns. And Roger Hickle Contracting got it for their price of $32.4 million, which was actually lower than the cost estimate, which was awesome because if you've been working lately, most things do not come in lower than the cost estimates. So that was great. We hit at the right time. for this to come in just under budget. Just before COVID was when this thing was bidding, so. Let's see, come on. So this is, you know, all grown up, adulting is hard, time to build it, right? So in construction administration, again, this is structurally slanted because I was out there taking pictures of the structure, not the other stuff. But we thought this one went really, really well. Overall, we were really pleased with how things went up. The questions were pretty minimal. The team worked well together, the contractor, the architects, the engineers, and the owner. What the design team was focusing on was reviewing all the submittals, steel package for their, and the rebar packages are the two big ones for structural engineering. So those went well. Responding to questions, helping with change orders. There were not very many change orders on this one, just a few things that they decided they wanted to add because they had a little more budget than they were expecting because the bid came in underneath. And then periodic inspections, like when we walked out and looked at this was just a look in the middle of construction. And then we did our substantial completions, which is the next one. So here's what things looked like when it was done. This is going to be one of my favorite projects of all time because you can see the structure, and you can see the mechanical ducting and other elements in the building, which is not something we get to do very often. That was really intentional from the part of the architect and the school district because this is a CTE school. And one of the things they're going to be teaching is construction and engineering services. They wanted the kids to be able to see it. So they left as much of the structure exposed as they felt like they could. They left, I have one picture I wish I would have included because it's got all the electrical raceways and everything down the hallways and it's all open. So the kids can see it and learn about it as they're going to school there, which is really cool. These guys are for acoustics, they're not lights, which are kind of cool, kind of interesting. So, and I put this one in here just to show that this is 3 buildings. From a structural standpoint, we have 3 independent structures that were all designed for their own drift and they all interacted like this. So what you're seeing here, the truss is on the admin side of the building. And this beam and this lower beam, these drag beams are on the academic wing side of the building. And they are not working together. They are intentionally kept separate, which the original building only had a 2-inch seismic gap, which was not enough. It was definitely crashing together in some areas. So give them some of that assurance too. So the gym trusses were kind of interesting. We were going to do, like our original design had joist girders designed by a manufacturer. We provided loads for them. So these guys up here on the top, these smaller joists, those, they would have looked like that, very similar to that in the gym, and we would have just been reviewing them. But when the contractors bid it, all the contractors going after it said, we've contacted the joist manufacturers and they are 2 years out now from being able to provide us with a joist girder. So this was the start of the supply chain issues. And so rather than doing the joist girders, we got on the stick and designed some trusses instead. So they have trusses in here, and to the greatest extent possible, that might be my next slide, we bolted everything in the field that we could. So for the only real welding that occurred out in the field on this job was right here doing the brace frames to the gussets. That welding happened, and otherwise everything was welded in the shop. So they didn't have to do it out in the field so that they could get kids back in school as fast as possible as part of the goal. So this guy over on the left, it's actually just a little canopy over electrical equipment sitting out in the back. And these moment connections all done in the shop. So we added, there were 5 pieces. So there were 4 columns that had beams attached to them and then a roof structure that was already put together, and they came in, bolted it all together and moved on. So our columns and our beams, they all had end plate connections and were bolted in. And like I said, the only thing they had to come in and do was weld on the BRBFs. And off we went when they painted. So kept things quick for the contractor and they only had the welders on site for a very short amount of time, the welders and the weld inspectors, and all of that went really well. So we're pretty happy with how that turned out. Here's a couple of pictures of those buckling restraint brace frames. It was kind of funny because they look really big sometimes. Some of them are 14 inches in the classrooms, and because we don't design the brace itself, right? So we're working with them during design, sending them design loads. They send us back what they want to do. There's options. There's different cores inside of these things. So we kind of did the back and forth and talked with the school. We assumed a 12-inch. They said it needs to be 14. You know, we're having these conversations with the architects at school, and they were like, "We love it. It's big. Everyone's gonna feel safe." So that was kind of the general. It's like we don't get to hear that as structural engineers. We're gonna add more columns. That doesn't happen, right? So we were pretty excited that the structure was being celebrated in this job. An interesting thing about the selection of what we were gonna do, there was a lot of trauma to the people who were in this building during the earthquake. I went out to several community meetings, and they're like, "We're not gonna have that like brick stuff again, right?" Because there were chunks of CMU definitely shaking loose and falling, and it was loud during the earthquake for them. A welding teacher, I talked to a lot of people that were in it, so just to kind of find out where people's heads were at and what was going on. And the welding teacher said he was in the middle of a welding demonstration, which he was really grateful for, that it wasn't the kids welding. So he was able to, but the lights went off immediately, right? So as soon as the shaking started, he's in the middle of welding. There's no more lights in there. So he had to get everything turned off and the gas turned off in the dark and then lead all the kids out of the building. Their emergency light didn't work in their classroom to show the exit. So they literally like daisy chained, like you see the kindergartners, right? And held each other's hands and got themselves out the back door of the building. So, and all the while they had like dust and debris falling on them, but luckily no big chunks. Definitely some scrapes and bruises because kids are trying, and in the welding lab, it's pitch black, right? It's dark in there, there's no windows. So that was an interesting perspective from him. And a lot of teachers that just like, there were teachers that couldn't get out initially and they're screaming for help for people to come get, it's an older building. There's doors that don't work properly and stuff like that. So it was interesting going out there and having a conversation with the community. They were kind of like, well, there were some like construction issues on the last one. How are we going to know that this one's not going to have those things? And so we were assuring the community that the process of plan review and permitting and construction inspection and all of that is different now, and people are paying attention. And I just told them, I was like, look, I got to stamp this. So I have, at the time I'm like, my kids are 13 and 9 now. So this is a few years ago. So it's like, I've got 2 kids in elementary school. And if they were coming to this school, like, I'm not going to stamp this thing unless I'd be comfortable with sending my kids to school there. So, it shouldn't take that from anybody to say that, but it definitely provided a little reassurance to the community that like, we're humans who do care, because sometimes people don't get to see that side of engineering. So it was great to get to go interact with the community because we don't get to do it very often. I think our architectural friends get to do a lot. They get out there and they do the planning. But on this one, we got to have a really good interface with the community and help make some of their fears go away. So we'll see if I can make this. I'll just show you the little video that Matthew made this.
I chose St. George's University School of Medicine because at the time that I wanted to go and work.
This is a CBS News special report. I'm Jeff Rohr at CBS.
That's awful. Do we want to try it again? How do I do it? Any ideas? I just wanted to play the video. Maybe we could even turn it off. Well, it is, but hearing it wise is what I'm after. That was pretty awful. Oh, right here. Yeah. This guy. It says it's muted. Oh, this. Sorry, guys. Those of you that the people in the room that know me are not surprised that I'm having technical difficulties.
Business headquarters in New York. A major
Yeah.
earthquake has struck near Anchorage, Alaska.
The quake measuring
7.0
7.0 has caused extensive road damage. At least one highway.
All right.
I don't know what that is. Just play it. It's just
Play it.
Several places. Our CBS
And
affiliate
KTVA was knocked off the air.
When the earthquake started, I was in charge of concessions at that point in time, and it was my prep, and I had gone down to set up for an event that we were having,
and the room was just filling up with dust and smoke, and I wasn't sure what, so I was trying to get out of that little tiny room, and it had a Dutch door, and I could not get the door open, and the earthquake just continued, and looking out into the hallway, what I could see, the ceiling was falling down, and the band kids came running out of the band room, they saw me trying to get out of the concession stand, so they stopped and jerked the door open and set me free. But it was very scary, and honestly, I was afraid that might have been my last day.
We did another sweep of the building, make sure everyone was out of there, and that's when we realized that probably the building's not going to be able to be occupied again. And that kind of started the whole journey about, like, you know, building a new school and demolition and funding and all those things. So, and here we are today in the school.
The school is just beautiful. I'm really looking forward to the kids coming in and seeing this beautiful space. It's been a real challenge for the last several years while we've all been squished together.
This is going to be the legacy of our, next generation of students, and so we're ready to make that happen.
And they still were finishing some of it after kids got there, but they did a really good job.
Most people have no clue.
Listen to this guy. The contractor did a really good job of focusing on the things. Can they not hear me now?
Yeah, they can't hear you all now.
Oh. So much for YouTube videos.
Let's see, can you hear us now? Okay, we're good.
Oh, awesome. But yeah, the main reason I wanted to show the video is it had the cool aerials of how it got built. And we thought it went really as smooth as any construction process that I've been a part of, which is saying something. There have been some good ones out there too, other ones. So some of our key takeaways as a design team on this one, especially from the structural side, was that the construction inspections are so valuable. I think it gets overlooked its importance of just getting somebody out there saying, yep, that's how it's supposed to be, or finding things that might look little that are not so little. And just having the right people who know what they're looking at. The other great thing about this project was that our clients really are often willing to do more than the code minimum on a project. I mean, you really could have gone into this school and seen the cracks in the wall and said, yeah, let's just back better that baby and move on with life and not look a lot harder. But the Matsky Brewer didn't do that. They said, we want to know, we really want to know. We want to know what's up with the school. We don't want to just put a Band-Aid on it. So let's take a look and find out. And when we did that, then they were like, you know, it's hard because the price tag was bigger than they were originally planning, but they want to do what's right for their teachers and their kids out there in their community, and they did. And here they are with a new school later than they wanted, but using a really awesome facility at the end of the day. So, and we found with a lot of our clients that if we talk about, you know, it's a risk category level 3 building required by the code, but we could make it a 4, and then you have a little bit more redundancy for your community in a, not just a seismic event, but a big wind event or big snow load that maybe collapses some roofs, something like that. You have more places to go that are built with more resilience. And we've found that a lot of clients are really willing to have those conversations and engage and put some money into those bigger picture things. And that's been, I feel like the earthquake helped that conversation within our community, but just brought awareness to the fact that we don't just have to do the minimum. And I think it brought awareness to the fact that the code minimum is not what people think it is, right? The code minimum is to make sure that people don't die, or rather to decrease the likelihood of loss of life. The code minimum is not intended to keep buildings standing in a massive earthquake. That's not the goal, because it is expensive, right? To design with that amount of.
It is designed to keep them standing.
It's designed to keep them
It's not
standing.
designed
Sorry,
to
thank
keep
you for the
them
correction.
usable.
It's not designed to keep them usable. Yes, they have to stand. Agreed. We're not letting them collapse. Standing after that day. So I think there was a lot of education that went on after the earthquake that was good for the entire community when it comes to new structures. And then I think the other one is just that replacing something is not always more costly than repairing it. And that was, we went down that road and got to look at both options and find out where it was that would be cheaper to replace it for the community. So that's what I have. Thank you. Questions? Yeah, what you got?
This is super interesting. I'm coming from a civil water sewer background, so
Okay.
the structural stuff is really cool, and the exposed frame and all that. Was kind of wondering, was there any site environmental, like prior contaminated sites, or the impacts that needed to be reconsidered for the new site, or?
You know, it was the civil side of things, there was really none of that really existed. They didn't have any issues on that front, really. And to be perfectly fair, I wasn't heavily involved in that side of things, right? So it wasn't the prime, but that I'm aware of, things went pretty smoothly on the civil front. We had one community member that showed up at every single community event and was like really, really concerned about the ground. And he's like, it has to be the ground. It's a geotech problem. They're not addressing the geotech. And really, we had the previous geotech reports and you could see like the ground is fine. Like there was very little impact on that front. We did pull out the entire foundation. And actually the soils out there were so much better than what we normally are building on in Anchorage. It's kind of wild, so we don't get to see that very often. But yeah, so on the civil side, not a lot going on there.
Yeah, the only reason I asked is like
Yeah.
it made it into ADN a little
Yeah.
while ago that their the public water well at Houston popped for.
At Houston High School?
Yes, at Houston High School, I believe popped for PCBs. if I remember
Interesting.
correctly.
Okay, well, I was not aware of that. And yeah, so that's interesting news to me. So I'll have to check it out.
And if I could steal one more question, you
Yeah.
mentioned the previous seismic gap was 2 inches. What are the new gaps?
These ones they're 6 inches. And I think the one, yeah, they're 6 inches. And we're like right where we are allowed to be. Like we started with an 8-inch gap and narrowed it to 6 as we got going. So, yeah.
Thank you.
Yeah. Did you have one too?
Yeah, your performance bonds and your payment bonds and their duration on a project looked to be maybe a little bit small, not long enough.
Oh, yeah.
Is there any, was there any recommendations made on that so as to hold the contractor and contractors liable?
Yeah, so the contractor actually was buzzing along right on schedule until we had that huge windstorm out in the valley. So the main reason that they ended up getting behind was because, well, like, for instance, all of the visqueen that you saw in some of those videos, it all blew out and away, and things that were not supposed to freeze froze. The elevator pit was 6 feet full of water and ice by the end of it. So they made a decision as a Matsu to shut down and reconvene and start after the winter season. So had that wind event not occurred, I do think the kids would have been in school when school started. So they had a second thing happen to them that caused their school to be delayed. But I think the Matsu's priority and the reason they did durations the way that they did was we want to get kids back out of portables, because it was a whole school of kids in portables, and back into the school. So I wasn't managing this project, so I can't really speak more to that, but that's my general understanding of how things went. We were definitely involved when the windstorm happened and the shutdown and making sure we weren't going to leave anything cold that couldn't be left cold and that sort of things. So does that make sense? Okay, what you got?
With all the exposed steel there and everything, aren't there some fire code issues? Did you have to do something special for checking the construction?
You know what, we talked about whether or not they had to be protected, and the answer was no. There's fire sprinklers everywhere that there needs to be, and the braces themselves are very well protected because they're actually inside a tube and inside concrete, the actual brace members inside. Oftentimes the column itself is the only thing that needs to be wrapped. And there were some locations in the building where the columns got wrapped because of that and they covered it. But then there are other locations where they don't have to be. So we did get into that early on in the design, and there are some that are wrapped for fire code and then a lot that didn't have to be. But man, it has been a long time for me to remember the specifics of the talks we had with the fire protection engineers on that topic. So you look like you got a question related to that.
I was trying to remember what.
Yeah, we did go through that extensively.
It has to do with combustion.
It does, and how much water and where the sprinkler heads are, and there's they do go out into the soffits underneath the canopies. I know that because we had to make sure that could happen so that, you know, but definitely a lot of talks relating to the sprinkler system and the columns and braces and everything else. So yeah, exposed structures. It's awesome. It says, so says a structural engineer.
What was total duration from time of quake to the substantial reopening?
I don't remember. I genuinely, I mean, we started at the end of 2019. So I want to say about 2 years, right around 2 years, maybe 2.5. So it was pretty quick for a facility of this size. Yeah. Yeah, it was 21. So yeah, it was about 2 years. It was pretty quick. Our design really did get done in less than 9 months. So we really went in and focused and had multiple staff members working on it. But like I said, this was from a structural standpoint, this is one of the easier ones I've done as far as coordination, because things were going to be exposed. It was going to follow a footprint that kind of already existed. So there were a lot of things that can take a lot of time up front that we didn't have to spend a ton of time. And that went for really all the engineering. You know, the mechanical was kind of like, you're going here. This is the space we have for it. Feed everything. It's like, go, 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 go. So it was quick, but it was reasonable. Like we felt like we did have enough time and got it done. So.
Have you had an opportunity to speak to some of the students or some of the people that were previously there about
I
the
haven't had a
facility?
chance to go present to the students yet, but it's in the works for sure.
That'd be cool.
Yeah, so we'll be excited to go do that, and we want to do and Roger Hickle did take some of the students and staff like through it while it was being constructed, so they got that look at it. And then, yeah, it's definitely in the plan for them to get some presentations and like a little more in depth than this, like from each of the different design disciplines to tell them about the systems that are in their school, and then we can walk around and show, right there. There's your buckling restraint brace frame, and here's how those work. So, yeah, definitely. Yeah.
You mentioned that the structure is redundant. How did you like analyze that? Did you take pieces out, or just redundant in the sense that it's extra strong?
So it's redundant in the sense that that's a good one. We have multiple frames in there, and yeah, we looked at some of it. We would pull one out and we'd do kind of a progressive collapse look at some of the things. We'd pull some of the members out and analyze it without it and look at the other way. And in some cases, it wouldn't take, like the one brace isn't going to take the big mega earthquake all on its own, but it can take, if one fails and then we have an aftershock, these can take some of those forces. So yeah, we did look at it, get some of the things in a progressive collapse format. The track in the gym, it has both hanging structure that supports it and moment frame connections for it. So if we lost one of those vertical connections due to, say, a basketball hoop falling and swinging and taking one out, there's a moment connection underneath that can pick it up. And so we tried to do those things throughout the building to provide some additional structural redundancy for them. So yeah, we had more conversations with the client on that side of things than I've probably ever had, because they were really interested in doing that type of thing. So it was great. Yeah.
Our secret password for our CEUs is one of those things that might be good to give out.
Dr.
And
what will you give me? The password for CEU is Houston, all lowercase. Pretty easy to remember, right? Houston.
I hope so.
So yeah.
All right.
All right. Thank you
Thanks, guys.
very much. That was excellent. One more question.
Yeah, in the course of your investigation, did you compare the seismic design values from the 79 or 82 UBC versus what we're getting now?
Definitely did that. Yes.
How did that compare? What were
their requirements were significantly lower. That Castle Mountain fault that's out there was not included at all. So they were designing to a lower code for sure. I want to say, I mean, not a double the magnitude, but like, yeah, 50, 60%, somewhere in that zone. Less force when you start looking at the lateral force resisting system loads. It was going to be on the order of 50 or 60% less. I don't remember, but that was one of the exact number. But it was like one of the very first things we did was put together a report for them of, you're going to be deficient right off the bat because of this.
Okay.
So that definitely had a big impact on it. Yeah.
So I think one of the things that is highlighted through this that we struggle with quite a bit is getting fees for inspections during construction, especially on the engineering side, and actually getting owners to agree to those fees and those inspections and see the value in that.
Yeah.
So have you or someone else in the industry been talking about doing a presentation where we highlight some of these real world examples where it's like, hey, if we could have caught this in construction and provided, $32 million in value for a $2,000 site visit.
Yeah. Well, I mean, the construction deficiencies, I mean, it's obviously in conjunction with the earthquake because it's been standing there doing its thing until then. So it's not all of that, but that definitely led to problems with it being replaced. So, I mean, obviously we had really great conversations with the Mat-Su Borough on this topic. I've talked to the Kenai Peninsula Borough about it too. We went and did we've done these types of earthquake investigations all over the place, right? And so there's a those conversations are happening and some of these, but formal presentations, no, I haven't done anything like that. Yeah. But I do think, again, the earthquake just, it brought it up. I mean, people talk about it, you get into meetings where you're scoping things, and these types of conversations are had way more than they ever were in the past, at least in my experience. So it's really nice that it wasn't a magnitude 9 that just leveled a bunch of stuff, and that we're able to see deficiencies and fix them. And I've talked with a lot of clients about New Zealand, because in Christchurch they had a similar thing where they had a magnitude, I don't know, it was a 6 something, 6 something. And then 6 months later they had a 7, which doesn't seem crazy, but it brought things down because they hadn't fixed things after. So we had a lot of conversations on that front where this is why you need to fix it now. I know that it's only partially damaged, but we could have another one at any time. And it doesn't have to be huge. You already have some damage. It's the proverbial, like, bend the paper clip how many times and it breaks. Like, every event we have takes the paper clip closer to breaking. And so you want to get in there and fix things when you can see that they're there and you can. And so I think overall, especially the public infrastructure has been listening and taking that conversation to heart and are fixing a lot of things.
Commissioning is also getting more popular.
Yeah.
Commissioning on this project as well.
Yeah.
That tackles kind of the same problems that structural C by doing like an actual in-depth investigation into the system operation.
Yep, making sure things are working properly, and sustainability of our infrastructure that's a popular topic right now, and it's a good thing happening. So
All right. Thanks, Amy.
okay,
There's
thank
a little
you.
more food in the back if you guys want it.